All right, so we want to look at something. This is kind of like a railgun. It's actually more or less the same sort of idea, but what we're going to do is we're going to turn the railgun into an elevator instead, which means we have maybe some sort of rolling contact here, and the current will come up this way, come across this way, right under the elevator, and then come back down this way. All right, so you'll be standing here. It's a very small elevator, and the current will provide the force that counteracts the gravity. So we'll have a free body diagram like this. Got a weight coming down, and the force from this particular model coming up. And what the idea is we want to know how we can keep this thing stationary, right? Now I say it's stationary on the third floor, but you'll look at this and you'll say, okay, well, if I've got a force and a weight, then this thing's zero if I want to keep it stationary, and the forces have nothing to do with the height, right? The force, the weight is F or W equals mg, and the force itself is going to be this geometrical factor k, which we're calling 1.5 times, what did I say it was? Mu naught I squared, right? So this efficiency multiplied by this thing will tell you exactly how much weight it can hold, and then if this current is higher than needed to balance this weight, it's going to move the elevator up, and if it's lower, it'll make it come down. And if the current goes off while the thing's actually operating, then the elevator will fall. So that's more or less what's going on. Now, probably you could introduce some friction or something in here so that you'd have a fail-safe, but we're not worried about fail-safes at this point. We're just worried about the elevator. It would be nice if this were a completely electric elevator and instead of having any mechanical parts, but you do have mechanical parts right here. These rollers, these connectors are mechanical, and so you still have failure mechanisms there. So let's go ahead and look at this situation and figure out what that current is that keeps this thing floating. Like I said, this F is equal to K mu naught I squared. I is what we were looking for. This is 1.5 here, and mu naught's what it's always been. And we need a mass, which is a 1,000 kilogram car, and G, which is, what will I use, 9.8 meters per second squared. So we have all of the data, we just have to plug numbers in. Okay, so we'll take K, that's 1.5. 3 halves, mu naught is 4 pi times 10 to the minus 7. And that we said is in Tesla per amps per meter. I is in amperes, but we just have I squared. Then we have mg, which is 1,000 kilograms times 9.8 meters per second squared. Okay, so then we have to divide things out. So we find I squared is equal to, this is 9,800 if we multiply 9.8 times, or 9.8 times 1,000, it's 9,800 newtons over 3/2. So we can cancel that 2, so it makes 6 pi times 10 to the minus 7 Tesla per amp per meter. Okay. That's equal to 519.9 square amps. Then we just take the square root, right? Square root of this guy, which is 22.8 amperes squared. There we go. So, nice direct line of reasoning going from our Newton's first law, free body diagram, using the approximate equation that I talked about in class and lecture, and then just plug a bunch of numbers in and do all the fun math, and gets us all the way down to 22.8 amperes to run that thing. So I wonder what amazing difficulties there are in this that make it even harder, because if it was just this, that sounds like it would be pretty cheap. So what are the issues? Obviously there was a safety issue, right? You don't have a cable holding the thing up. A pneumatic elevator, you have something on the bottom pushing it up. In this case, the only thing that's keeping this afloat, keeping this from falling, is the magnetic field driven by the current coming this way. Right, so that current is going around like this. Got another current going around like this. That's interacting with this current here, which is pushing this up. So sounds like a useful thing to have happen, but there must be a problem with that somewhere that keeps people from using it. All right, bye now.